Next, we have Barun, Acharya and Rudraksh Pareek, software engineers. They will be presenting on queuing up security for multi-tenant cloud infra at scale. Their session will explore Kubernetes job scheduling challenges and how Q addresses this for AI ML security workloads. Let's welcome Barun, Acharya and Rudraksh Pareek to the stage.
Hello, everyone. Session just before the coffee. I know you have been listening to too many sessions. You might need a coffee break. So we'll try to wrap it up quickly. It's called Queuing Up Security for Multi-Tenant Cloud Infrastructure at Scale. We'll go through all of the aspects, why multi-tenancy, why security, what's queue, all of those throughout our talk. A bit about ourselves. I'm Barun Acharya. I work as a software engineer at Accuknox. I lead the team for a project called Kuberenetes. It's a CNCF sandbox project, and I'm a CNCF ambassador.
Hey folks, I'm Rudraksh. I am also a software engineer at Accuknox, where I'm working on orchestrating runtime security, and I'm also a maintainer of Kuberenetes, and I mentor in programs like GSOC and LFX for the Kuberenetes project itself. So, you know that we are going to be talking about security today. We'll be having a specific focus on cloud security. So, we know that modern workloads, they are getting cloud-based. You deploy on cloud, and you might be using some cloud APIs as well, and there are coupling with cloud things, and so on. So, what this does is it makes the applications, your workloads, very dynamic. Plus comes the fact that the infrastructure that they are running on is dynamic as well. And you need to secure these things if you didn't know till now. So security will need to adapt to this new thing, basically the dynamics that have been introduced through moving workloads to cloud and all. And since there are many moving parts, it becomes complex to do security. There are a lot of things to secure, a lot of things to scan, and so on. And one of the parts of that is like you have to do security on a regular basis so that you can ensure that you are compliant with frameworks or anything that your organization recommends. So yeah, now this is a landscape of many security tools. This only includes the cloud native security tools, and if I would have to include the cloud security tools like Cloudsploit, Steampipe, then this landscape wouldn't have fit on the screen. So we only have these. Most of these are open source. You can pull them in, you can use them on their own. And when you see this, you might be thinking that, oh, this is so huge and I'm so confused. Like, what should I do? So how do you handle this?
So, too many tools, too many things to secure. So you need to orchestrate, you need a way to orchestrate all of this, right? So I have maybe 10 tools for me. Say I'm running AWS for myself, and I have 10 tools like Steampipe, Cloudsploit, Tracy, Macy, lot of tools like that. For right now, we are taking that, okay, we'll have 10 tools. So we need 10 jobs to execute that, okay? There will be 10 tools scanning my AWS infrastructure, that if I'm still compliant, if I have any security vulnerabilities, or what's my current security status. But I don't only have AWS. Like AWS is not a single entity. I have my S3 buckets, I have my ECR registries, I have my EKS cluster, ECS. Let's say we have 10 assets. And now these 10 assets will be running with 10 across all these 10 tools. That gives me 100 jobs to schedule. But let's just say for like, okay, you won't have a single Kubernetes cluster. And taking a more realistic example, you would have maybe 20 assets to scan and 200 jobs to schedule. We at Accuknox not only just run these jobs to know about the reports, we also want to normalize all of this data so that you know meaningfully about what what the security tool output is, how do they compare across all the say you have a container and multiple tools reporting different kinds of vulnerabilities with different CVIDs. How do they interrelate? What's the normalized result? So all those reports are also part of this scanning. Plus, we are maybe doing this for 100 customers. So Now we have 600 jobs across 100 customers, 60,000 jobs to schedule. So jobs to schedule, more than 50,000. But this is not like, okay, I run it once, I forget it. As Rudraksh pointed out, we need it to be, we need our infrastructure to be continuously compliant. So we'll maybe run it every few hours or few days, depending on what's your scale, like how dynamically your CI/CD pipeline push to your infrastructure and update things. So 50,000 jobs to update every few hours or few days. And how do we deal with that?
So we at Accuknox, like when we came with this problem statement, what we did was we created this architecture, and it was salt stack based. We had this scheduling system where our APIs, like we had an API call that would put jobs in RabbitMQ. Queue. They would be simple messages, and then these messages will be consumed by a Celery. Celery will then schedule it on similar, like we had a fixed number of nodes, and we'll be scheduling those jobs on those nodes. Basically the salt minion master mechanism architecture. So what happened was when we started to scale at the 50,000 job level, when our number of customers increased and all that happened, we started facing problems around sharing the infra and like isolating our tenants. Basically, there will be different jobs for different tenants, and there will be a lot of them. So we are a security company ourselves, and we need to make sure that the data of all the customers that we are scanning the cloud accounts for, that is separated. So we need to maintain this isolation between our tenants, jobs, and all that. And another issue we faced was there was no easy way to track the status of the jobs that are being run in these nodes. So that was another problem. And then sharing resources, like we could not track the CPU usage, we could not limit that, and similar problems related to the compute resources that you have. And this was specific to us, like the nodes that we used to run on, they were not so reliable, and they used to go down, and we faced problems due to that. So if we sum these problems up, like it comes to, we had problems with multi-tenancy, and we had problems with managing jobs, basically job objects, might be cron jobs that we had to schedule. And then we had, this just turned off? Okay, it's fine. So then we had problems with, and then like, as we needed to use resources efficiently, we had this problem, like we needed to auto scale, we needed to increase the number of resources that were allocated, and resource management was something similar that we wanted to efficiently use this. So if we take a look, then this boils down to these. And does this sound familiar? Like what tool does all these things? What simplifies all these things? If you think about it, it's Kubernetes. Like you can use Kubernetes to solve all these kind of problems. And how? Basically, we used Kubernetes. I guess you all know what is Kubernetes. It's an orchestrator at its core, and it started at Google. The purpose was around job scheduling itself, so it's the perfect tool for it. However, the features that we benefited from, like particularly in Kubernetes, were namespaces. So we were now scheduling the jobs in different namespaces, like to achieve multi-tenancy. And then like Kubernetes has these inbuilt cron job objects, which allowed us to schedule based on like out of the box. We didn't need to take care of the cron ourselves. And resource sharing, we know that there is CPU and like resource limits on the Kubernetes objects themselves, and auto scaling operators and all that exist, so that we can, based on the resources used by our things, we could scale and add new nodes and schedulers. So you might be thinking that, okay, like good solution, Kubernetes will handle it all out of the box, it's magic, it should work. But that did not happen. Basically, when we were trying to do this, we simulated an environment where we created a lot of jobs. We went through what has been done for this in the past. And there is this guy, if you know, Kueue-ing guy, he does experiments with scaling with Kubernetes. And he has done this, like he overloaded the Kubernetes, and by running 50,000 jobs and pods, what happened was he faced problems like HCD running out, it limiting the number of pods that were being able to create, and other problems as well. You'll find the video on YouTube. So basically, we faced problems with running raw Kubernetes jobs. More specifically, one thing that was the jobs are like sent at once. That won't be possible because HCD does not accept them. So we took this solution that we'll send jobs batch by batch. And this is similar to like what we were doing earlier. We were queuing up jobs. And this would require setting up an intermediary broker queue that existed for us before as well. But now we would have to take care of like having it as part of Kubernetes as well. Like our Kubernetes scheduler should know what jobs we want to schedule, and our APIs will need to take care of that as well. So it became a complexity to manage all this. Then other thing was enforcing order. Deployed batch jobs in Kubernetes, like by default, they get in random order. There's no specific order. But we had this use case where we wanted to prioritize certain tools to be run for certain customers. And we couldn't do that with raw Kubernetes jobs because there is no priority, no FIFO, nothing. We could have gone to this way, like using some hacks around it to make sure that priority jobs are scheduled first. But again, that was very hacky and it was not very reliable. And other thing was we were not able to like efficiently enforce limits on the resources, and we were not able to share them. So you might be thinking, okay, you have told me about your problems, you have told me about your architecture. What should I do? What did you do? So Barun, please tell us the answer.
Okay, so the answer was in the talk title itself. We'll use queue. We have been talking about queuing up jobs in some manner or what. But there's a project inside Kubernetes SIG called Queue with a K, like every other Kubernetes project. So what Queue is, it's a KH native job scheduler. It can handle multi-tenant job infrastructure. It can schedule jobs. It can help you preempt. It has cohorts. It has a concept of cohorts, borrowing, preemption, all the features that we wanted to do. I don't want to, so like at the end, this was our solution, but how are we using it? Let's take a look at it more from a feature point of view. So Queue has certain features. It has internal batch scheduling mechanism. It knows that it does not need to overload HCD. So it takes care of that on its own. That okay, how much it can monitor, because it's running inside the Kubernetes cluster, it has access to all those metrics and behavior so that it can accordingly batch schedule so that things are not overloaded. It has the concept of preemption that, okay, I have a priority job to run now, but I am not sure, like, okay, if I can kick out other jobs, you can define certain things that, okay, this is a, because in priority comes that which is more of priority. Is job A more priority, job B more priority? There are a lot of complex handling there. Queue has an efficient way to handle preemption for that. It has resource usage called cohorts. We'll take a live example for that. Crucial to us was auto-scaling through cluster autoscaler. So we did not need to implement any of our own APIs to understand how to and when to scale. Queue natively integrates and provides out-of-the-box metrics. If you want to, you can plot those metrics out in a Grafana dashboard or a Prometheus, like extract through Prometheus and plot it on a Grafana dashboard. But you can use them, integrate with cluster autoscaler and say, we needed more nodes. We can tie up a node autoscaling to this metric and it will scale up. At the end, as a user, none of your flow changes. You deploy a like set of jobs. The only change is that you add an annotation saying what's the queue name it is supposed to be in, and you keep it as suspend true, because you are leaving queue to know when it should not be suspended and when to run it. So queue automatically handles when to run it and when not to run it. All other things are handled by queue. It will admit it. It will inject node affinity based on whether nodes are available or not. There's a job controller, which then it's all Kubernetes native. Again, there's a job controller, you have a scheduler, you have cluster autoscaler. All of these entities are Kubernetes native, so you don't need to worry about that, okay, there's some third-party infrastructure managing my jobs. It's just that queue is managing when to deploy your jobs, and it has its own custom CRDs which on top of which it decides on. So say some of the questions around are, what if I use a custom scheduler? People write their own custom schedulers for various reasons, especially for ML workloads. So the scheduler itself is not changed, so you are free, you don't need to worry about that. At the end, what queue is that internally you deploy this job. Queue has its own one-to-one mapping to say what's the workload doing. It has a one-to-one mapping. Through this workload, it knows whether a job is active, job is inactive, when to schedule it, is it finished. And then a number of workloads are associated to a local queue. This local queue is tied to a namespace. And finally, there's a cluster queue where multiple local queues can bind to, or you can choose to keep it one-to-one as well. So talking about how we designed around queue, this is our infrastructure on what all features do we use for queue. So we have a shared cohort. This lets us define, say, I have a total capacity of 1 lakh jobs. I've designed that, declared that 1 lakh jobs as part of this. Then I have cluster queues saying, say, I have a priority tenant. I have a big client paying more. So I decided to dedicate a cluster queue to him. But then I have certain other clients, maybe they have their schedule is maybe one client runs at 5 p.m., one client runs at 10 p.m. So because their schedules are like aligned like that, I can decide to run them on the same cluster queue. So client B and C, tenant B and C share their cluster queue. Cluster queue is just a resource for me to define how many jobs can run in this. Because I'm defining that just to highlight, because these are still tenant B and tenant C, and they have their own independent namespaces. None of their information is getting shared. This is just for, from a resource perspective, what can be scheduled, what cannot be. Now inside, we have the same concept. We have a local queue. We can define a workload priority. Priority jobs get admitted. There are normal scheduled jobs. How do we decide what's a priority job, what's not a priority job? That's for, we'll take a look at it from a diagrammatic point of view. So let's say I have a high priority tenant. I have 2 jobs running in that. And I have the other tenant's queue, and my job queue is full. It was designed to handle 100 jobs. It is handling 100 jobs. Now I have 101 job. What do you think will happen? It will move all the, however capacity of the high priority tenant is, it will move all those back here. So we have decided that borrowing limit for a high priority tenant is 4. But now my high priority tenant, so let's stick to just other tenants for now. So I have a priority job in this other tenant, and both of my queues are full. Who do you think will be kicked out? Out of which queue? Any guesses? Nope. So the priority job will be, because priority job is associated with the other tenant, it will kick out one of the jobs in this priority, in this queue, and your job is now like this. This goes back to the suspended stage. But now, similarly, a normal job comes up, and it sees that wherever I am supposed to stay, it's all occupied already. So I've defined that preemption within cluster queue. I can preempt lower priority objects, and I can reclaim within the cohort. So any cluster queue, I can choose to reclaim it. So because this tenant itself has a higher priority, it will kick out the job from its own queue, so that job can stay in suspended stage. But the queue has the feature, because it's just preempted. In case of Kubernetes, your pod might go just, it may just forget to reschedule it again, because the pod went into an error due to lack of resources. But in this case, queue has an efficient way to put it back to suspended mode, and it will handle it like whenever things get free again, it will push it back. So that's all for the like how we at Accuknox use Q. Just certain takeaways are security is an ongoing process, so that you don't you cannot run it once and forget it. If that was the case, maybe you could have just run it on your own laptop. You would have a dedicated person, system administration who will run all of these jobs for you once a day, and that's fine. But because this is an ongoing process, it needs to be tied up to your CI/CD pipelines, or the schedule needs to sync with whenever you deploy your new jobs, and accordingly run your scans. Kubernetes jobs can be used to schedule these scans, but there are certain caveats when you run them at scale. That's where Q comes in to help you orchestrate it in an efficient way, and while maintaining isolation for multi-tenant workloads. And it helps you streamline things for you. So that's all. Thank you. We are from the Kubearmor team, so you can check out Kubearmor on kubearmor.io. Barun.cc is my portfolio. Rudraksh P is his portfolio website. Give us a star if you like, and we are open for questions.
Thank you. That was a good one.
Thank you.
So Kubearmor, do you run this as a SaaS offering?
Kubearmor is a product. It's a daemon set that runs on, it's an agent that runs on your cluster, like Kubernetes cluster or Linux, or anything on top of Linux, it can run in there. So there's an enterprise SaaS product for that, but Kubearmor itself isn't just an agent, and it has all the capabilities of just like what it is supposed to do, that is runtime security enforcement.
But all the analysis that you said, for example, the architecture that you showed earlier, all of that happens in your own environment,
Yep.
correct?
So that's on top of the data that it sends out.
Yes.
So analysis of that data. So Kubearmor itself is just an agent
Yeah.
that runs. So like there are tools out there which utilize. So Kubearmor in general is a different. So like it's different to what we were talking about. The talk was more in line with what do you do out of, so like compliance scans.
Yeah.
This is a tool to help you enforce compliance, but then you need a report, right? That, okay, if I'm compliant or not. So that's the talk.
So what you showed is after you get all the data, how you process that. And when you do this, for example, let's say you are doing this for a AWS, customer running AWS workloads. Where does this happen? Does this analysis happen in another AWS environment, or does it not matter?
So it does not matter. So at the end, so there are two aspects. One is generating the data. So that can run, provided you give us the cloud account access and all. Read-only access is fine as well. We'll run as part of our infrastructure, or you can send it to our API. You can run, like depending on certain customers don't like that, okay, we share UCase, we will only share whatever the output data is, filter it out and send you. So we'll take that data and schedule a job to like normalize that data. So those are the two aspects. Because even if we are SaaS service, we provide on-prem support as well. So you can take this entirety of architecture and run it as part of your on-prem setup as well.
Thank you. Last question. Q, does the scheduling aspect and all of that, can that be externalized to a database?
Can you add some more details? Like, I'm not sure what you're.
So there are other scheduling systems, right? Which read the scheduling data from, let's say, a database or a file system. How does this queue work? Is it doing all of that inside a Kubernetes cluster, or can some aspect of that be externalized, is the question?
No, so this is entirely meant for a Kubernetes. Yep. So this is supposed to be it is tightly coupled with Kubernetes. So because you see, it is orchestrating the job object itself. So this is not supposed to be run outside of that. So you can manage your Kubernetes infrastructure in any way, have a custom scheduler. If this scheduler itself can tie up to a database, that's a different thing. Queue is not a scheduler for like your pods and like actual resources on Kubernetes. It helps you manage the entities for job. Its only role, if I had to simplify a lot of things, its only role is that it sets suspend true and suspend false for a job object. And then Kubernetes itself decides whether if suspend is set to false, how and when I run it. So that's the point. Hope that answers your question. Any more? No? Thank you. You can find us here in the conference. Come say hi, talk to us about anything cloud native or security. That's all.
Thank you, Barun and Rudraksh, for the amazing session. Now let's welcome Govind, our track captain, to hand over a token of gratitude.